graphs of functions. And I think where I'll start is let's introduce one type of function that we've already really seen. That's a piecewise function. And talk about how you can graph them by just thinking about how to graph each of the pieces. So here's one. The absolute value function is a piecewise function. And what are the three different types of numbers that absolute value treats differently? If x is positive, how do you compute its absolute value? You just give that same number back? Yeah. So one of the pieces of the absolute value function as a piecewise function is, well, if x is bigger than 0, then the absolute value of x is just x. All right, how do you read that? You read that as the absolute value of x is x if x is positive. What other types of numbers are there other than positive numbers? Yeah, let's see how that one. Negative. If you have a negative number, how do you compute absolute value of x? You can throw an extra negative sign in front to cancel out the negativeness that x already has. If x is less than 0, then the absolute value of x is just negative x. And there's one other type of number. If we know what to do with positive numbers and negative numbers, is there a number that's not positive and not negative? 0. What's the absolute value of 0? 0. Cool. So if x equals 0, absolute value of x is just 0. There's a prototypical example of a piecewise function. A piecewise function is any type of function that has different types of behaviors depending on what type of number you plug into it. And here's maybe a more made-up example. Let's think about the function f of x, which is equal to x plus 2 if x is less than or equal to 0. Strictly less than 0? Strictly less than. F of x is equal to 1 if x is between 0 and 1 inclusive. And f of x is 1 minus x if x is bigger than 1. So let's just put that into plain speak words. This is a function, and in order to evaluate that function, well, first ask yourself, is the x value you're plugging in less than 0? For x values less than 0, f of x, or if you're thinking about graphing, maybe you would say, well, that's the y value, is equal to x plus 2. For x values between 0 and 1, inclusive, f of x equals 1. So for x values between 0 and 1, if you were to graph this thing, you would just see a y value of 1. And finally, for x values greater than 1, f of x is 1 minus x. Now let's try to graph this thing, right? This is a rule. If you give it any input value, you can always find an output value. So it's a function. Maybe just to hammer that home, let's suppose I gave you that piecewise function and asked you to compute f of 5. What would you need to do? Well, alternately, just what is f of 5? Let's see, that value 5, let's see which of the buckets it falls in. If you take an x value of 5, is that x value less than 0? No, so the green case doesn't matter. Is that x value between 0 and 1? No, so don't care about the blue case either. Is that x value bigger than 1? Nice, so that means f of x is 1 minus x. So I should take that 5 and plug it in for that x. which is? That seem okay? Whenever you have a piecewise function, you can evaluate it. But that's just what it means to be a function. Let's try to graph this thing, and the way I'll espouse graphing it is let's just graph each piece one at a time. So let's start with this. Let's try to graph x plus 2, y equals x plus 2 on the graph to this graph. And let's just do it by plugging in some numbers. If you plug in x equals 0, what do you get for x plus 2? 2. And I'm not going to worry about the whole piecewise graph yet. So that means this should be on the graph of the green function. -1. -1 plus 2 is 1. Plug in x equals 1. Plug in x equals -2. Plug in x equals 2. Nice. All right, so let's just try to sketch those points. Plug in -1, we got a y value of 1. Plug in an x value of 1, we got a y value of 3, which is off the graph. Plug in an x value of -2, we got 0. That seems pretty convincing. And I'm doing it in dashes because I don't actually care about that whole graph. So there's just the graph of that green function. Let's play the same thing for the blue function. If you have the function which is always 1, then what do you get when you plug in x equals 0? 1. All right, if x equals 0, then 1 is still 1. In fact, what are all of the numbers in this whole column? So what does that mean over here? That means for absolutely every x value, the y value is always going to be 1. So that blue function is y equals 1. The green function is y equals x plus 2. And that last function, 1 minus x. Let's play the same game. Plug in x equals 0. What do you get? Plug in x equals -1. What do you get? 2. Plug in x equals 1. And maybe that's even enough. At 0, we get a y value of 1. At -1, we get a y value of 2. At 1, we get a y value of 0. Yeah, that looks like it's just going to be a straight line. So far, so good? So right now I've got 3 separate functions. But I don't want all 3 of those functions. I want the graph of this function. So to get that, let's just think about where we care about each of those functions. The green function is x plus 2. For what x values do I care about x plus 2 in this function? X values that are less than 0. So that means I care about this green function only for x values that are less than 0. So there's x equals 0. And I only want x values less than 0. So there's the green function, but only for x values less than 0. Where do I care about the blue function? Between 0 and 1. So let's highlight that. I need the blue function, but only for x values between 0 and 1. Now let's think about endpoints. Should I put like solid dots or open circles at those endpoints? Solid dots, because those endpoints are actually included. This is a, well, I've done too much. There's a less than or equal to there, a less than or equal to there. So those should be solid dots. And where do I care about the pink function? Greater than 1. In fact, just for the rest of the x values, right? So here's a strategy to graph a piecewise function. start with the graph of each of the pieces. Hopefully they're easy to graph. Then just figure out where you want each of those pieces. And this isn't terribly readable, so maybe just for the sake of cleanliness, let's just copy that down over here. So you see this downward facing line, maybe I'll just arrange that it has the right intercepts. When x is less than 0. And now the color coding matters less, but I'll still do it. So this right here is just the graph of y equals f of x for this particular function. That feel pretty okay? So there's the whole philosophy of graphing piecewise functions. Graph each piece, put them all together. And now, well, it says depending on time, and I'm clearly past time because this was supposed to happen on Monday. But let's just see if people want to do another example of this. Would people like another graphing a piecewise function example? Cool, let's do it. So let's graph this piecewise function. Let's sketch the graph of f of x equal to x squared minus 4 if x is negative, 0 if x is 0, and 4 minus x squared if x is bigger than 0. And in order to help, I've already provided the graphs of each of those pieces. And maybe we'll start by color coding. So x squared minus 4 is the upward opening parabola right here. Yeah, let's use this one next. 4 minus x squared is this downward opening parabola. So now here's the game old thing. Where do I care about each of those functions? Copy down that graph for those inputs. Well, what inputs does this graph care about the pink function? Well, x value is less than 0. So that means that the pink graph, I only care about that for x values that are less than 0. So I only care about this pink function for x values less than 0. So that's like that part of the graph. And I guess I'll want to exclude that because 0 is not less than 0. Where do I care about the blue part of the graph? X value is bigger than 0. And 0 is also not bigger than 0, so I'll exclude that endpoint. It looks like I don't have anything over x equals 0, but take a look at that function. What do you get if you plug in x equals 0? 0. In fact, that's literally just one of the instructions. If the input is 0, spit out 0. So what other point should I highlight on this graph? The origin. 0, 0 is on the graph because f of 0 is 0. All right. I know that result is definitely not like what you'd want to plot it, so it's a little bit too messy. Right? Like when I did it, you could tell which of those was supposed to be highlighted, but now maybe you can't. So this is why I provided a second graph to use. So I cared about the pink piece, which has this open circle here. It seems to have an x-intercept at -2, and then it looks parabola-y from there. There's a solid dot at 0, 0. Now I'll copy down the blue piece. People feel pretty okay about that? So especially if you're already given each of the pieces, Here's an algorithm caller that just graphs any piecewise function. Start with each of the pieces, decide where you care about those bits of the graph, highlight them, and then just copy down the bits you want. Any questions before I start in on a different topic? Cool. Let's start doing some linear functions. So here's a definition. What is a linear function? And maybe well, I don't know. What do you think? When I say a linear function, what do you think that should mean? I have an idea of what I want to write, but whatever you say, if the word linear is a reasonable logical thing, should be what comes to mind. Yeah.
The rate of change is all slope.
Yeah. Slope is unchanging. Maybe I'll drop a more technical sounding word because I'll use it a few times. What does it mean to not change? It means it's constant. Yeah, that seems pretty good. I guess we haven't defined what slope means, which, we already have an idea of what slope should be. That seems like a great definition. It's not the one that I will write down in a moment. What else would you want this linear function to be? Yeah, maybe not the function is line, but this graph is a line. Nice. So here's the definition of algebra, which is the same as those two. So if those two are the ones you want to keep in mind, that's fine. A function that can be put into the form f of x equals mx plus b with m and b constant. So the pink one is the one that I'll actually treat as the definition. A linear function is something you can write in the form f of x equals constant times x plus a constant. That number m turns out to be the slope. Let's explore this. Here's a function, f of x equals 9/5 x plus 32. Is that a linear function? Yeah. And you can check the other things by maybe like doing some graphing, which, in fact, maybe we have already. Does that graph look like a straight line? And whatever slope should mean, it shows like that slope is the same no matter where you go. So I think they all agree. So it looks like it's linear. If you want to put it in this form, what are m and b? Yeah. Awesome. That's correct. But for this particular example, b is 32, and m 9/5. And I didn't just pull that formula out of nowhere. Does anyone just like recognize that from something that they do occasionally? Celsius to Fahrenheit. Yeah, it's Celsius to Fahrenheit. Yeah, not Fahrenheit to Celsius, Celsius to Fahrenheit. And we'll explore that in a minute. Like, it's not important that it's that, but. Next one, g of x equals x times x plus 1. Is that a linear function? Anyone want to say yes? Anyone want to say no? Cool, why not? Yeah.
Because the m as a variable.
The m has a variable. Were you going to say something similar?
Yeah,
it sure looks like this has m equal to x, but this is not constant. So this bit at the end, which seemed like it may have just been a throwaway with m and b constant, is actually pretty important. The m and b have to be honest to God constants. So is this linear? No, it is not. Next one, h of x equals 3. Is that a linear function by our definition? Pause for a moment. And let's see. Folks who want to say yes? Anyone want to say no? All right, those who said yes, what's m? 0. All right, you could rewrite this as 0 times x plus 3, right? Anything times 0 is 0. So m equals 0 and b equals 3. And this is why I included this bit. It's anything that can be put into the right form. It doesn't already have to look like y equals mx plus b. If you can do some algebra and get y equals mx plus b, it's a linear function. And maybe just to hammer that home, here's another one. 2y minus 3 equals 4x plus 5. Does that give y as a linear function? Folks want to say yes? Folks want to say no? Yes. It is. I think it is. That means we should be able to put it into the form y equals mx plus b. So I guess that means if we get y on its own, the thing on the other side should be constant times x plus a constant. So if you want to get y on its own in this equation, what seems like a good first thing to do? Add 3 to both sides. You'll get 2y equals 4x. 5 plus 3 is 8. All right, what next? Divide both sides by 2. And whenever you divide both sides by 2, you have to divide, oh, that pen just popped right apart. All of both sides by 2. Giving you y equals 2x plus 4. Nice. So what's m? What's b? Groovy. And entirely by coincidence, I've graphed those same functions off to the right. And let's just check the other thing. So there's y equals 9/5 x plus 32. That graph look like a line? Yeah. And right, the hash marks are multiples of 10 instead of multiples of 1. You should include that if you're including a descriptive graph. But all I care is that it's a line. It's a line. Y equals x squared plus 1. Not the graph of a line. So this one was not a linear function. It's graph, not a line. There's the graph of y equals 3. Would you say that looks like a line? Yeah, it's a horizontal line. The last one, 2y minus 3 equals 4x plus 5. Look like a line? Cool. So, no surprises here. You already told me that linear functions are the things that have graphs equal to lines. That's why they're called linear. Now let's focus on this word slope, which, oh, yeah, thank you. So I guess you've already told me that, like, m should be the slope, right? You've already told me that. What does the slope mean? Yeah, great. Yeah, what's that? Yeah, cool. It's how much the y value of the graph changes divided by how much the x value changes. It's rise over 1. So the slope of a line is given by, I'm going to start by just writing a few words. Slope, also called rise over 1. Maybe I'll also say average rate of change. And now that we have all those ones written, maybe it makes sense to just write down the formula. It's the amount that the y value changes divided by the amount the x value changes. And maybe I'll write down one other thing that will just seem purely symbolic. A lot of times when a mathematician wants to refer to the amount something changes, that mathematician will put a capital delta in front of it. The origin for that is entirely just what variable was the appropriate old dead European chose for this symbol. There's nothing deep behind it, just history. Is y, so it's the change in the y coordinate, y2 minus y1 divided by x2 minus x1. So if you can find 2 points on a line, you can find the slope of that line by computing that difference. And like you've already told me this, m should recover the slope. And let's just check that that's consistent using this example. Y equals 2x minus 4. What should the slope be? Let's just check that that's correct by plugging in some inputs. I'll plug in an input of 0 and 1. If you want to check another pair of inputs, go for it. So let's see what happens when x equals 0. When x equals 0, what do you get for y? Cool. I just didn't want to do it myself. I'd probably get it wrong anyway. What do you get when x equals 1? All right, so now we have 2 points on the line. 0, 4 is one of the points, and 1, 2 is another one of the points. That's enough to find the slope. The slope is given by y2 minus y1 all over x2 minus x1. And all right, like on the one hand, there is what the slope is. Should that be like simplified probably? Yeah, what does that simplify down to? Slash, should I do it? Cool, what is it? 2. And I suggested that maybe you would do the same thing using a different pair of points. Did any folks plug in a different pair of x values? All right, so let's bring it back to this first thing that was said. The slope should be just a constant. It shouldn't depend on where you check the slope, if this is actually a line. Whenever you have a line, which 2 points you use to compute the slope won't matter. They'll all give you the same thing because they will all give you this parameter. Neato. Seem pretty okay? Good. All right. So here is an opposite direction too. So linear functions are called linear because their graphs are lines. And in fact, with like only one type of exception, every line is the graph of a linear function. There's exactly, well, kind of exactly one exception. What is that exception? Orbital length. There's the line x equals 2. Is that the graph of a function? Or not? It fails the vertical line just like really badly. So it's not the graph of a linear function because it's not the graph of a function. All right, but with only that exception, most lines are, any other line is the graph of a linear function. And in order to demonstrate that, let's think in terms of this. So any line is specified by just what 2 points does it go through, right? You draw 2 points, you grab like a straight edge, you draw the line between them. If you don't have the straight edge, then probably you'll be drawing what I would say passes as a line, but it won't look very straight. Let's try to do that. So let's try to think about the line between 1, 3, and 3, 2. Maybe we'll even like draw those points and draw that line. 1, 1, 2, 3, 3, 2, 1, 2, 3, 1, 2. So line will look something like that. Let's see if we can find an equation for that line. So I guess that means I want something in the form like y equals mx plus b. And let's start with that m. That m is supposed to be the slope. Do we have enough information to compute the slope? Yeah. In fact, how many people just have already done it? Nice. Should I actually go through the walk of computing this slope? Cool, but I'm just going to pause for a moment, and you will tell me what the slope is. I hear a -1/2. Voices of agreement? Any voices of disagreement? Anyone want to see the computation done? Cool. And maybe we'll even check by looking at this. Does that look like it has downward slope? As x goes to the right, the y values go down. It looks like it's not so slopey as being like slope -1, so I think -1/2 is consistent with that picture. All right, so that means we know something. We know that this equation will be of the form y equals m, -1/2 x plus b, where this b I still don't know. I still want to know it. And maybe I'll use this philosophy. No, yeah, this is fine. I'd like to know what that b is. How can I discover what that b is? Yeah. Yeah. I know that each of those x values should correspond to the corresponding y value. Yeah. Could I plug 0 in for x? I think the only shortcoming is I don't like already know what should happen. That being said, once we do this, we will know what happens when we plug in 0. So let's take one of those 2 points. I think 1 theory looks easier to use just because 1 is a simple number to use. Should get the same thing no matter which one you use. So let's plug in x equals 1, y equals 3, and see what happens. We should get 3 equals -1/2 x, which is 1, plus this unknown quantity b. That look easy to solve for b? What do you get? In fact, literally 3.5. You would add the 1/2 to the other side. B equals, and I think I'll write this in a few different ways. I'll write 3.5 as that because that is a notation that you see. I don't like that notation because I see that notation and it makes me think 3 times 1/2, which isn't what you mean. Maybe there's a form that you can actually tell what it means. Alternately, you could write it as a single improper fraction, as 7/2, I guess. Neato. So, it looks like we wind up with y equals -1/2 x plus whichever one of those you like best. That feel pretty okay? So there's another philosophy we could have used, and it's maybe even one that I kind of meant to use. Let's think about point-slope form for a second. So point-slope form is just another form you can put a linear equation into. any linear equation can be put into the form y minus y0 equals m times x minus x0, where m is the slope, and x0 and y0 are a point on the line. And let's just go back to that previous example. The points y we computed the slope to be -1/2. Do I have at least one point on this line? Great. Let's just plug that in for the x0, y0. Which point do you think I should use? Theoretically, it doesn't make a difference. I guess we used 1, 3 for the other example. Let's use 3, 2 this time. So the equation we get will be y minus y0 is equal to -1/2 x minus x0. And I don't know, maybe we should just finish that out and get y on its own. What would you do to get that into the form y equals mx plus b? Move the 2 over. Y equals -1/2 x minus 3 plus 2. And that's a perfectly fine answer. Is it of the form y equals mx plus b just yet? What should we still do? Yeah. Nice. -1/2 x. Double negative will become a positive, plus 3/2, also known as 1.5, plus 2. Is that the same answer as we just got? Cool. We get y equals -1/2 x plus 3.5, which we already got. That feel pretty okay? Cool. All right, so there's a general philosophy here. Whenever you have 2 points sitting on a line, you can figure out that line. And there are the 2 philosophies that we've just emphasized. First things first, find the slope. And you know how to. Slope is the rise over one of that function. So compute that. If you're using this philosophy, put the thing in point slope form, solve for y. The other philosophy is plug in one of the given xy values, and then solve for b. So, there's nothing fancy there. If you want to find an equation for a line, you can. Here are 2 philosophies that let you do that. And yeah, we got time to do one last one. So you already told me that this formula on the previous page gives the conversion from Celsius to Fahrenheit. And there's nothing terribly fancy about that formula. Let's in fact rederive it. So this example will have you derive the conversion from between degrees Fahrenheit to degrees Celsius. It's a linear function, and here are some given facts. 0 Celsius is 42 Fahrenheit. You already knew that because that's freezing. -40 is the same in both systems. I guess there's one other thing you should just know about each of those. This isn't a math fact. This is just a temperature fact. What's something else about Fahrenheit and Celsius? hot does water boil? 100 Celsius. And Fahrenheit? 212. But you know, we'll get that in a minute. If you're boiling water at standard temperature and pressure, and you know what? Maybe we'll like check that using what we get at the end. All right, so let's get a conversion between Celsius and Fahrenheit. And you know what? I'll even give you a point of decision. Would you rather convert from Fahrenheit to Celsius or from Celsius to Fahrenheit? Fahrenheit to Celsius. Celsius to Fahrenheit. Cool. So let's find a conversion from Celsius to I was very careful about when I wrote this, how you actually spell Fahrenheit, because again, it's just some old dead European's name. Same with Celsius. Let's try to find this formula then. So if I want to go from Celsius to Fahrenheit, I guess that means that I should treat Celsius as the input value, so the x values, Fahrenheit as the output values. So if I want to try to sketch this on a graph, I would want Celsius to be the x value and Fahrenheit to be the y value. So what 2 points should I put on this graph? Zero, 32. And what other point? Negative 40, negative 40. I'm not trying to be careful to like draw that picture to the right scale. I'm just trying to draw a picture. And the conversion is going to be a straight line. All right, let's find an equation for that line. Step 1, find the slope. Good. Looks like everyone's just already doing so. And maybe I'll even say these numbers look like they're going to be big enough that you might resort to a calculator. Not saying you have to. In fact, it's not. Numbers aren't that big. Cool. What'd you get? I would regard that as correct, but not simplified. 72 and 40 have any common factors? At the very least, they're both even. They're both, in fact, I think pretty clearly multiples of 8. So let's pull out those common factors and see them cancel. 72 is 8 times what? 40 is 8 times what? So this simplifies to just 9 over 5. How many folks just got to 72 over 40 and then like took out a calculator and got like 1.8? That would be fine. Yeah, that's not an unreasonable thing to do. All right, so we have the slope now. Let's find b. Which of the 2 points given seems like it would be easier to use?
0, 32.
0, 32, I think. And like x equals 0, well, I guess it's c equals 0, but maybe x and y is good for now. Y equals 32. So what will this equation become? It will become y equals 32 equals slope 9/5 times 0 plus b. Cool, so what's b? In fact, did you need to do anything to solve that? Yeah, in fact, how many people would have done that without, in fact, writing basically anything? Yeah, cool, because of something that will write in one of these two spaces. So the straight line is given by y equals 9/5 x plus 32. Or, going back to what the actual symbol should be, the temperature in degrees Fahrenheit is equal to 9/5 temperature in Celsius plus 32. Cool. Do any people feel particularly stubborn and obstinate instead go the other direction, finding conversion from Fahrenheit back to Celsius? Okay. You could have, right? It would have been the same amount of walk. All right, so let's close with, I have 2 minutes, talking about x and y intercepts. And let's just remember this really quickly. How do you find the x-intercept of a graph? You set y equals 0. So let's do that for a line. So to find the x-intercept, you plug in y equals 0. That look like something you could theoretically solve for x? Yeah, we could. I won't. How about the y-intercept? How do you find the y-intercept? Set x equals 0. And let's see what that does for a line. Y equals m times 0 plus b. For a straight line, what is its... Oh, wait a minute. Yeah. For a straight line, then, for a line y equals mx plus b, how can you just automatically get the x-intercept? Whatever b is. And that's for the x-intercept. The y-intercept, right, like you can solve it, but you don't get anything particularly compelling. So here is a useful fact. The line y equals mx plus b has y-intercept at y equal to b. Or I guess 0b if you wanted in like Cartesian coordinate form. So, this is where I'll stop because I'm at time. There's homework to do tonight. At some point later today, if you haven't opened the web homework, I'm going to go check on that. And if you haven't, you'll get an email that will either read as concerned or annoyed. I'll try to write it so it comes off as concerned, but it's hard to get something as ephemeral as that intent to eliminate. Thank you.
No, this is literally the very first one, and it says it's wrong. Is that right? If it's wrong, it's good. I just thought it was right. So.
Oh.
Not positive. No, I'm going to send both of them.
Yep. So they're certainly consistent. Those two are the same. Let's think about what is not positive means.
Less than 0.
Not quite. That's what it means to be negative.
Isn't that not positive?
It's almost the same. Think about 0. Is 0 positive?
Yeah.
0 is not positive. Yeah, 0 is the thing you're missing.
I got
Does that now make it clear how to fix it too?
Yep.
Awesome.
Thank you.
Yeah. Hello. Good. Yeah, you emailed me, right? Nice. Let me start by giving you some things. So, the way I run my lecture is very much as going through a set of notes. We'll start around there. If you want to catch up, you can take a look at what's in there and decide how much catch up you want to do. One thing that I do is I post to. Are you on Canvas yet?
Yes, I am.
Awesome. Have you seen this webpage yet?
I have not.
Okay.
I will do some investigating for sure, though.
Yeah, so you can, on one hand, you can get there by like Chris Davis, Matthew, WEC, and you'll find it.
Okay.
There's also a link from Canvas. There's like a module item that says something like welcome in some logistics or something.
Okay.
And it'll get you there. And the things you'll see there is a day-by-day breakdown of like what's going on each day.
Okay.
Some suggested textbook problems that I don't collect. And I also record each of my lectures, and you can find those links to these. Okay. They're not like high entertainment, it's just, I think the camera sees.
Okay. Is the textbook required for class? In class?
I will give you warning for any days that I do really want you to have it, because
Okay.
I know that it's very heavy, and
It
I don't
is.
want you to blow out your back.
Okay. Perfect.
Yeah, and this document, which I'll hand out in pieces as we go, it's like a 200-page long PDF. This is what I really treat as the cross textbook for those things.
Okay, perfect. And
All
I
that.
will start doing some of the homework.
Nice. I might even give you a copy of the syllabus just because I have some.
Okay. All right, well, thank you, sir.
Yeah, thank you. Hello.
So, I have been stuck on the September 8th open-ended homework on the very last problem where it's asking f of g of x. And g of x is x minus 1 over x plus 1. And I plugged that all in. I tried to figure out how to solve it, but I couldn't find the answer. So, could you run that?
Yeah, so, yeah. So you got x minus 1 over x plus 1.
Yep.
Wow.
1 over x minus 1, x plus 1, so that's x minus 1. Cool. So I kind of got stuck with like trying to figure out like a common denominator and all that.
Oh, nice. And we certainly could do. But how much does it say, like, simplify it out all the way? Is that one of the...
That and then try to figure out the domain from that.
Cool. Let's do the domain first. The domain you always check before simplifying. Okay. So to figure out the domain, let's just think about what bad could happen. So just by looking at this piece, what bad thing could happen?
You could get something over 0.
To get something over 0. So that better not happen. What about this? Could anything bad happen?
You could get this entire thing over 0. Actually, you could probably get this over 0, and that would be fun too.
Yeah, so it's so this whole denominator could be 0.
Yeah.
So this is like bad twice. And also all that could be 0. Those look like things that you could figure out what x values they correspond to.
Probably, yeah.
Okay, cool. Won't do that here. It looks like there might be 2 gaps in the domain, but maybe this results in also the same as the other one. It might be. Let's talk about how to simplify this. Let's start by just focusing down there. If you just saw this and wanted to simplify, what would you do?
Probably add 1 to the other side.
There's no other side.
Okay, never mind.
Like there's no
Yeah.
equal sign.
I would. I honestly don't know.
So whenever you see like a fraction minus a number, you should think to yourself common denominator. So to get a common denominator, just in that green bit, what would you do?
If I multiply x plus 1, I'm not thinking straight today.
That's all right. So I'll leave everything else alone except that group.
You don't have an official practice.
This is still.
Oh, yeah.
And now we have a common denominator.
Right.
So how do you add fractions? Well, I guess subtract. How do you subtract these fractions?
You can just put that all together, can't you? So you can, x would just get, would that just be 0 over x minus 1? Because negative 1 and positive 1 cancel out. No, but then you're subtracting the positive, so it'd be negative 2 over x plus 1.
Yeah, I think that's right, but you've also done too many things at once for me to be like, so, like, it's all going to be over x plus 1. And on the top I'll see x minus 1 minus x plus 1. 12. And then let's just talk this. So I guess you're convincing me that this is going to be like negative 2.
Yeah, because x gets canceled out, x is subtracting x, and then negative 1 is subtracting 1.
Yeah.
So we did that, and then after that, we jog down to the bottom of the drill from the feet.
And let's just recall this bit about them too. So how do you divide by a fraction? What does it mean to divide by a fraction?
Dividing by less is 1.
Sure, but like, how does, there's another bit of simplification. How can you simplify that?
Is this where you multiply both the top and the bottom by the bottom?
Yeah, kind of. Whenever you see like 1 or 1 or 1, 2, you see that's the same thing as 2 or 1.
Right. Okay, so
You guys were like behind the film camera.
So that becomes just x plus 1 along negative 2 for you.
okay.
And now you see something similar. So this fraction minus that fraction. Now do it again. Cool. Is that helpful?
Yeah, I'm gonna take a picture of this. That's okay.
Yeah. And the thing to remember is, like, you still have to always check domain before you simplify. Neato. So I guess it's pretty close to time. Yeah. And today is